Hello and welcome to Notes 11.2 in BC Calculus. We're going to cover the integration when we have an indeterminate result. So quick little review. We have indeterminate forms whenever we have a 0 divided by 0 or an infinity divided by infinity. And as you recall, we used L'Hopital to get out of that a while back. A few other indeterminate forms are when we have infinity minus infinity, or 0 times infinity. And then there are some somewhat special cases when we have 0 to the 0 power, or infinity to the 0 power, or 1 to infinity. Those are indeterminate forms. So if we get this in an integration, then we're going to need to apply some of these rules that we're going to talk about today. As you recall, if I integrate from a to b of some function f of x, we'll take the antiderivative, evaluate that at b, the antiderivative, evaluate that at a, and find their distance, their difference, excuse me. Now, if f is continuous, this will work. And also, remember, it must also be closed for this to work. So if these conditions aren't met, then it's going to be an improper integral. So an improper integral or proper integration occurs if f is discontinuous. We have something going on in our domain that causes this function to be discontinuous, or if the interval is left open, we have something going on at one of the ends. Either a is going to infinity or b is going to infinity. Next, we know if we integrate from a to b, we can split this integration up and integrate it from a to some value c between a and b, and then add the integral from that same value c to the upper bound b of f of x with respect to x. And also a quick little limit reminder. If we have a limit of a composite function, what we can do is just take the limit of the inside function, evaluate that, and then take that result and input it into our outside function. So, quick little review. Now, let's get into what we're going to concentrate on today, and that's the idea of tests for convergence. Some improper integrals may be very hard to determine whether they converge or diverge. Therefore, we're going to need some tests. These tests for convergence are very useful tools when handling these improper integrals. The first test we're going to talk about is called the p-test. P is just short for powers. Anytime we have some value of x to some power. This is a useful test for improper integrals to determine if they converge or diverge, which are of the form that looks like this: 1 over x to some power p, as long as p is some real number and p is greater than 0. I won't go through this and do this for you, but I encourage you to graph these. You can put those in your graphing calculator. I think the best way to view these is to go to desmos.com and then just put in each one of these functions as they are and just take a look at those graphs. Just zoom out and look as x goes to infinity, see what happens. And then also look at it as x goes to 0. That's going to really help you with understanding what we're going to do next. So I'd go ahead and pause the video, go to Desmos, enter these in, and just kind of zoom around with those. It won't take but a few minutes, but it'll help you understand these improper integrals that we're going to look at. Okay, so first of all, let's take a look at our first set of examples. Oh, better remind you, this is, again, an issue that most of you won't have, but some of you will. And that is the idea that AP says if you have any improper integral, if you have no limit, then it's easy for them. They give you no credit. Don't need to grade it. They just look at it. No limit, no credit. Okay. So let's take a look at our first one. You can see B is infinity. This is definitely improper. So make sure we get the full credit by saying the limit as B goes to infinity of the integral from 1 to B of 1, well, I guess I'll put it as power rule so we can see it, x to the negative 1/3 power dx, an easy integral to take. Remember, we haven't taken the limit yet, so we still need to show that we need to take the limit. We add 1, multiply by the reciprocal, evaluate this from 1 to b. The limit as b goes to infinity, I'll factor out the 3 halves and then put in here b to the 2/3 minus 1 to the 2/3. Now we can evaluate this integral, and we know as b goes to infinity, this is also going to go to infinity. Infinity minus 1 is going to be infinity. Therefore, this diverges. Let's take a look at our next example. Same thing, b is going to infinity. So I'll write the limit as b goes to infinity from 1 to b of x to the negative first dx. That, of course, is our natural log of the absolute value of x, antiderivative. We still haven't taken our limit yet until we have substituted in b. So this will be the natural log of b. b is definitely a positive number. It's going to a positive infinity, so I can drop those absolute values. And of course, we're doing the natural log of 1. When I evaluate this at infinity, the natural log of infinity is infinity. And of course, the natural log of 1 is 0. So for the second time in a row, we've got infinity or something that diverges. All right. Let's take a look at our third example. B is still the upper bound that is going to infinity. So we'll rewrite this. And again, use our negative exponent so we can quickly see our exponent rule. The limit as b goes to infinity, antiderivative, add 1, multiply by our reciprocal, and evaluate this from 1 to b. That means the limit as b goes to infinity, when we, again, factor up, get that fraction out of the way, so it's nice and easy for us. This will be 1 over b to the 4th, negative 4th power when we substitute in b, and then we'll subtract 1 over 1, or just plain old 1. Now when we evaluate this as b goes to infinity, 1 divided by infinity is going to be 0. So this is going to be negative 1/4 times negative 1, or we get 1/4. This one actually converges. Okay. So if you looked closely at your graphs up here, you would notice a little bit of difference on those as you went to infinity. All of them are pretty close. They've got that butterfly or right side of the volcano shape. But if you zoom in on these at infinity, you'll notice that some are getting closer to 0 and some are not getting close to 0. And that will help you understand what we're going to, what we found out with these 3 examples. You'll see in our first example here, our p-value. Remember, we're using this form here, 1 over x to the p. Our p-value here is 1/3. Our p-value here is 1. 1 over x to the first power. Our p-value here is 5. 1 over x to the 5th power. Okay, so p-value of 1, p-value of 5, p-value of 1/3. And what we'll find is with our p-test, memorize this here. When we have horizontal improper integrals, so remember those were the type 1s where we looked horizontally at infinity out here. We're looking at this end. And remember how we just kind of talked about improper as area in here. We're going from 1 to infinity, and that area, if it has if it doesn't close down fast enough, then the area kind of oozes out is what we might want to consider here. Okay? And indeed, we have a rule that we can apply here with our p-test when p is less than 1, and very important here, make sure you're looking at this, we're evaluating from 1 to infinity. When we are less than 1, this will always diverge. Always diverge. And technically, I guess I should put this as between 0 and 1, but that was defined up here above. We have to be greater than 0. Next, if p equals 1, that was this case right here, we will find out that in that case, we also will diverge. And then finally, if p is greater than 1, and again, we're integrating this from 1 to infinity, then in this case, it will always converge. And as a matter of fact, we can actually calculate the value that it will converge to. It will always converge to 1 over whatever our p-value is minus 1. Our p-value is 5. It converged to 1 over 5 minus 1, or 1/4. Okay. So again, make sure you kind of see this. When we're going, when our p-value is between 0 and 1 and we're integrating from 1 to infinity, it's not going to close up fast enough for us, and we're going to diverge. If we equal 1, you can see we ended up with the natural log function, and that one will diverge. Quick little note, you'll see that we can evaluate from 1 to infinity. And if we are evaluating this curve, here's 1, and we're going to infinity. And let's just say that this converges. We did our test, and we found out that that converges. Okay? So in other words, it closes on down, and we're good to go. We can get a value out of this. Okay? Now, if I take that same function, but rather than evaluating it from 1 to infinity, I choose some number here, a, and evaluate that to infinity. Well, I think it goes without saying that you can easily see that obviously if we're converging from 1 to infinity, 1 to infinity converges, then a to infinity, as long as a is greater than 1, then this will obviously converge. And obviously it's going to converge to something a little bit less than the 1 to infinity. Okay. Let's take a look at 3 more examples. One more reminder, AP still has this rule. It hasn't changed no matter how good you think you are with calculus. If you have no limit, they don't care. They're going to give you no credit. And the same thing with me. Any homework, quizzes, or test that has an improper integral with no limit will have no credit. Okay, let's take a look at our next set of examples. You'll see this time we're integrating this from 0 to 1. Key point here. We're integrating this from 0 to 1, a little bit different than we did on the previous page. So this time you'll see when we start here at 0, 0 in the denominator is going to cause us a problem and make this improper. Therefore, we have to write the limit as a goes to 0. We'll do that from the right of the integral from a to 1 of x to the negative 1/5 dx. Let's add 1 to our exponent and multiply by the reciprocal. And let's evaluate this from a to 1. That means the limit as a goes to 0 from the right, factor out the 5/4, and we'll have a to the 1/5 power minus, oops, got that a little bit backwards. Sorry about that. Got a spammer calling me over here. Sorry about that. So I need to evaluate this at 1 to the 1/5 power minus a to the 1/5 power. Of course, 1 to the 1/5 is going to go to 1, but as a goes to 0, a to the 1/5 will be 0, and we'll have 1 times 5/4, or 5/4. This one converges. And let's take a look at our next example. Same problem. We'll have to take the limit as a goes to 0 from the right of x to the negative, integral from a to 1 of x to the negative 1st power dx. This is, again, our natural log antiderivative. So this will be the natural log of the absolute value of x evaluated from a to 1. The limit as a goes to infinity from the right of the natural log of 1 minus the natural log of a. Of course, we know the natural log of 1 is 0. Sorry. And when we evaluate the limit as a goes to 0, remember our natural log graph is the one that looks like this. So as we go to 0 from the right, we're going to a negative infinity here. Negative infinity times this negative is going to take this to infinity, which is going to tell us that this will diverge. Let's take a look at our third example. We have the same issue, limit as a goes to 0 from the right, integral from a to 1 of x to the negative 4th dx. Antiderivative by adding 1, multiplying by the reciprocal, will give us x to the negative 3rd times negative 1/3, and we'll evaluate this from a to 1. The limit as a goes to 0 from the right, factor out the negative 1/3. This will be 1 over 1 to the 3rd power, or just 1, minus 1 over a to the 3rd power. When a goes to 0, it's really, really, really small. 1 over a to that really, really small number is going to give us infinity. So this one goes to infinity and diverges. So let's summarize these three examples just like we did on the previous page. In our first one, our A value was 1/5. The second one, our A value was 1. And on our third one, our A value was 4. In these three examples, we have our vertical improper. You can see from my quick little sketch here, we're improper on all of these as we're going to 0 from the right. We get this area that's spewing out vertically from that. When we see this, and again, this is the integration from, make sure you see the difference between the previous ones. This is from 0 to 1, not 1 to infinity. When we go from 0 to 1 and P is between 0 and 1, then this one will always converge. And as a matter of fact, we can calculate that. You can kind of work backwards maybe from this formula to see this, but this is always going to equal 1 divided by 1 minus P. Okay. So in this previous example, our P value was 1/5. 1 minus 1/5 would be 4/5, and 1 over anything is the form of a reciprocal. So the reciprocal of 4/5 is 5/5 in this example. When our P value equals 1, this will always diverge. If our P value is greater than 1, like 4 in our example up here, this will always diverge. So again, from integral from 0 to 1 in this power form, where our power is in the denominator here, 0 to 1 will converge. 1 to infinity will diverge when P is less than 1. And just the opposite with P greater than 1. When we take the integral from 0 to 1, P is greater than 1, we will diverge. If we go from 1 to infinity, then this one will converge. P, whenever P is 1, doesn't matter if we're going from 0 to 1 or 1 to infinity, that will always diverge. Okay. Quick little note here, the p-test can be used to decide whether it's worth trying to evaluate some improper integrals because they're expected to converge, or not because they're going to diverge. Okay, so simple little test. Now, a little bit of a variation from this one is our e-test, and it's kind of a special one. The e-test is used whenever we have something that looks like this. It's basically the exponential decay graph. Okay, so whenever we evaluate from 0 to infinity, a little bit different than our p-test, and we're of this form e to some constant times x, where the a, that constant, is less than 0. In other words, it's negative. Then this will converge. Simply put, this is an exponential decay graph. And that exponential decay graph will converge. Okay? And as a matter of fact, if our a value is equal to -1, we have the special case here where this, believe it or not, converges to exactly 1. Let's go through a couple quick examples here. Hopefully this will make this permanent for you. Okay, so first of all, now let's take a look at this, and you can see we need to apply our p-test. Our p in this case is 3/7. We want to know if this converges or diverges. Well, first of all, you can see that our p is less than, oops, why did I put 0? It's less than 1. And we're integrating from 1 to infinity. Okay? So we're going from 1 to infinity, kind of going in that direction. But our P is less than 1. If you'll look back at the previous chart, you'll see that this combination is not a good combination if we wanted to converge. This one is going to diverge. Don't need to do any analysis of it. I can quickly use my p-test, say it diverges, and move on. So that's the nice thing about the p-test. And again, that was summarized in this statement up above. Okay. Let's take a look at our next one. In this one, our p-value is 5/4. So this time, our p-value is greater than 1. And if you look here, we're integrating this from 0 to 1. If you'll look up above, this combination, p greater than 1, integrating from 0 to 1, is a recipe for a diverge. This integral will diverge. Don't need to do anything. Just move on to our next problem. I'm not sure why I've got an extra E in my diverge, but if you want to put it there, go ahead. Let's take a look at our next one. In this one, our p-value is equal to 21/17. 21/17 is, of course, greater than 1, and we're integrating this from 1 to infinity. Since we're greater than 1 and going from 1 to infinity, this one will converge. Next case, you'll see that p equals 1. We're integrating this from 0 to infinity. So our p-test doesn't handle that, but our p-test does handle from 0 to 1. And we can evaluate that from 1 to infinity. And that covers both of our p-tests. But unfortunately, since p is equal to 1, this will diverge and this will diverge. So the whole thing will absolutely always diverge. Let's take a look at our next one. We have a similar situation that we just had. In this case, our p is equal to 2, but we're evaluating this from 0 to infinity. So we need to break this up from 0 to 1 over x squared dx, plus the integral from 1 to infinity of 1 over x squared dx. In both of these cases, p is greater than 1. But in the first case, we're integrating this from 1 to 0. And the second one, we're integrating it from 1 to infinity. This one is nice, and that results in something that converges. But this one here resulted in divergence. And since we're adding these two together, the divergence is the one that's going to overpower, and therefore this will always diverge. Let's take a look at the next function. Okay. In this case, we've got a odd function here that I do notice. Odd function means we can rewrite this and evaluate this from just the right side, excuse me, from 0 to infinity of 1 over x to the negative third power dx. Okay. And if we look at this, we'll have to split it up into a 0 to 1 and a 1 to infinity. this case, we could show that this one converges, but unfortunately from 1 to infinity here, with our p-value being less than 1, this one will, and we're going from 1 to infinity, this one will diverge. Therefore, the combination will result in divergence. Next one, we're evaluating this cosine from 0 to infinity. And this one, as you recall, is going to have that cosine graph that is always going to be oscillating back and forth. So due to the oscillation, this one will diverge. No need to do any fancy p-test at all. Okay. Next one, you'll see that we do have a hole in this one at x equals 4. But this can factor out. We know that this is going to be an x minus 4, x plus 4. Factoring this out, we'll integrate this from 2 to 8 of x plus 4 dx. The hole occurs at 4, and we would need to rewrite this as the limit as b goes to 4 from 2 to b of x plus 4 dx plus the limit as as a goes to 4 from a to 8 x plus 4 dx. Looks like I've run completely out of room here, but hopefully what you can see here is this is just going to be a line. Probably didn't even need to go that far since we weren't asked to actually find the value of it, but we know that this would be a line that had a y-intercept of 4. We're doing the area underneath of that, and at 4 we have a hole. We're integrating this from 2 to 8, and remember what we said about holes. Holes just result in just one little sliver that's immeasurable, that we're undefined at, so therefore this will converge. No need to use my p-test or the e-test on this one. Let's take a look at a couple more examples. In the next one, you'll see that we've got a 1 over x minus 3. And what I'd prefer to do on this one is to think of this as that shift. So if I think of this as my lower bound 3, I can think of that as 0 plus 3, and the upper limit as 1 plus 3, 1 over x minus 3 dx. And you can see that that helps me understand that I could rewrite this as the integral from 0 to 1 of 1 over x dx, which is an easy one to see that it diverges because my p equals 0, and it doesn't matter that I'm going from 0 to 1 or 1 to infinity. This one's always going to diverge. In the next example, if I want this to get to an e-test, I can think of this as I'm putting in these negatives all the time. Well, let me rewrite this and integrate this from 0 to infinity and make this e to the negative x dx. It's going to do the same thing as this. negative infinity, negative a billion, negative a trillion, or a million, negative 1,000 as I go down. I'll just change the sign when I substitute it in. It's going to give me the same area. This one is an e-test. And you'll see that in this case, my a value equals -1. And that was that special case where this not only converges, but we know that it's going to equal 1. It's going to converge to 1. And let's take a look at our next one. In this one, we have 1 over, well, obviously in this one, our p-value is 1/2. That's that square root. And let's go ahead and rewrite this as the integral from 0 to 1 over x to the 1/2 dx plus the integral from 1 to 3 of 1 over x to the 1/2 dx. If we look at just this one here, our p-value is less than 1, and we've got the combination of integrating from 0 to 1. Therefore, this one will converge. This second part, remember we've got 1 over square root of x. It's going to look like this on that side. So we already evaluated from 0 to 1 of this right here. And by our p-test, found out that that converged. And then this part here from 1 to 3, well, that obviously is going to be a closed-in area. This one's not even improper. So this one will converge just because that's what we've always been doing. Area under those curves, we got a bound of the x-axis, bound of the function, a bound of the line x equals 1 and x equals 3. Therefore, that converges. When both of these converge, the whole thing will converge. Let's take a look at our next one. In this case, we've got a 2/3. So our p-value here is 2/3. Since this is being squared, this is going to act like an even function. Therefore, this can be written as twice the integral from 0 to 1 of the 1 over x to the 2/3 power dx. That means that our p-value being less than 1, and we're integrating from 0 to 1, gives us the right combination that this will converge. Okay. So again, all these examples, we weren't doing a full analysis of this. We were just determining, will this converge? Will it not converge? Okay. Next one is a show that problem. So let's show that this will equal the or pi divided by 2. So first of all, we don't have a problem at 0. We will have a problem at infinity. So this is improper when we look at our upper bound of b. So we'll rewrite this with our limit. And you should recognize that this is an inverse tangent antiderivative. We'll evaluate this from 0 to b, which means the limit as b goes to infinity, and yes, I still need to write that. I haven't evaluated the limit yet, even though I'm putting in the b in here, minus the inverse tangent of 0. Okay. So let's think about this. When b goes to infinity, okay, remember tangent is sine theta over cosine of theta. So when b goes to infinity, that means our cosine is the one that's going to go to 0. And we know that cosine goes to 0 at 1/2 pi. And likewise, this is going to infinity. If we evaluate this at 0, that's when our numerator sine goes to 0, and sine goes to 0 at 0, which means we have shown that this integral from 0 to infinity will equal pi over 2. Got a few more examples to do here, which have a little bit of mix in our integral solving techniques. Okay? So let's take a look at the first one. You'll see right away, it sure looks like a U substitution to me. I see e to the negative square root of x. So I'll try U substitution first. U equals negative square root of x, which means du will equal negative 1/2 x to the negative 1/2 dx. I do see a dx and a x to the negative 1/2, but I don't see this negative 1/2 in here. So let's go ahead and multiply both sides by negative 2. And now we have, I'll even rewrite it like they have it, so you can clearly see that all of this gets replaced with negative 2 du. Since I have a definite integral from 0 to 4, I do need to make sure that I use the u values in my integral here, not the x values. So when x equals 4, u will be negative 2. When x equals 0, well, u will still be 0. So I'm going to replace the dx over the square root of x with negative 2 du. I'm going to replace the negative square root of x with u, and of course use the proper bounds here of our integral. This negative 2 goes with our du, and this simply becomes e to the u. Can't get any easier. Oops, not sure why I didn't put the 2 in there. I put the negative, but not the 2. Next, when I look at this, I see that I'm going from 0 to a negative number, which means I need to rewrite this as a positive 2 and switch these from negative 2 to 0, e to the u du. And this one is not improper, so I don't have to worry about any of those problems we had with proper or improper. So let's go ahead and just put e to the u, evaluate this from negative 2 to 0, factor out the 2, e to the 0 minus e to the negative second power, which simply becomes 2 times 1 minus e to the negative second power. Let's take a look at our next one. I think you guys can quickly see from this one that we've got a function times another function. Don't see a quick and easy u substitution with this negative e, but sure looks like a uv prime, and since this is an x squared, I think it's set up for a tic-tac-toe. But before we do that, you'll see that we are going to infinity, so this is improper. The limit as b goes to infinity of this thing has to be written first before we start any tic-tac-toe. So let's take a look at this one and do our tic-tac-toe. So derivative, derivative, and derivative. Antiderivative, which then is going to become a positive, and then it's going to go back to a negative here. These are the antiderivatives, these are the derivatives. And then don't forget, we're going negative, positive, negative. Then the tic-tac-toe, here's these guys, and these guys. We'll have three terms in this. And this will be written as the limit as b goes to infinity of negative x squared e to the negative x, and then negative minus 2x e to the negative x, and then again a negative minus 2 e to the negative x. All of this is going to be evaluated from 0 to b. Let's substitute in our b values here. Limit as b goes to infinity, and this will be I do notice here that each one of these has e to the negative x in it. And so I'm not going to evaluate that with each one of them. I'm just going to put all of these over e to, in this case, e to the b. So this will be a negative b squared minus 2b minus 2. And then I'm going to subtract, well, when I put in 0, these two guys are both going to be zeros. But this one, e to the negative 0, will just be 1 times 2. So this will be minus 2. Okay. Now, as I look at this, I can see that this guy, e to the b, is going to go to infinity. B squared minus 2b minus 2 is also going to go to infinity. So this is going to result in an infinity divided by infinity, which means our good old buddy, L'Hopital, is going to come into play. So let's go ahead and take the derivative of this guy. This will mean the limit as b goes to infinity of negative 2b minus 2 over e to the b minus, or actually plus 2 over there. We still have b going to infinity and e to the b going to infinity. So we still have an infinity divided by infinity. So L'Hopital is going to come out and be used again. This time we'll have negative 2 over e to the b plus 2, which of course, as b goes to infinity, this is going to go to 0, which means we have 0 plus 2, and this equals 2. Done. All good. Let's take a look at our next one. You can see that this one has an issue at x equals 0. We've got this natural log function, which is this guy, but since it's an absolute value, we've got this going on. And we're evaluating it from -1 to +1. And so we got to figure out, are we going to be able to close this up or not? Okay. Now, I do recognize that I can simplify this a little bit, because this is obviously an even function. And so let's just evaluate this from 0 to 1 and then double it. Okay? So we've got to rewrite this with the limit as, a goes to 0 from the right of this 2 times the integral from a to 1, natural log of the absolute value of x dx. This one is one of our memorized antiderivatives. So this will be the limit as a goes to 0 from the right of 2, and then this will be x times the natural log of x minus x evaluated from a to 1. Let's go ahead and substitute in our a. so we can evaluate this limit. Oops, this is 0. So 2 times a times the natural log of a minus a. Oh my goodness, I did it again. This should be 1 times the natural log of 1 minus 1, which of course this one's part's going to go to 0. Sorry about that. I evaluated a, not the upper limit. So these are all 1s there. Minus, now I'll put the a in, a, natural log of a minus a. And we're evaluating this as a goes to infinity. And remember, again, this is a little messed up in here. So this is going to 0. This will be a 0. Oops, wait a second. I see a 0 natural log as a goes to 0 from the right. This is going to be times a negative infinity, which is an indeterminate form. Not so good for us right now. So let's take a closer look at this and see what we can do with this. So first of all, I've got 2 times all of this in here. So I'm just going to, just for the sake of cleaning things up, I'm going to factor this 2 out in front. So this is the limit as a goes to 0 from the right. In here, this one was supposed to be a minus 1 in here. So this is minus 1. And then I've got this 0 times infinity. And remember, what we tried to do sometimes was put this into a form that we could use our L'Hopital. And it sure looks like I could probably factor out this a, which is what I am going to do. So this will be negatives out here in front. The natural log of a, negatives are getting me a little bit screwed up in here. So let me just put plus. I'll put a negative there, and then minus 1. Do something like that. Oops, no, I've got this negative here. That would be a plus 1. Okay, and then I'm going to rewrite this all divided. If I factor out the a, I'll have to write this like this. Okay, so you can see this is a nice little technique we did with L'Hopital, where we rewrote this as a rational function, multiply it by the reciprocal, would be equivalent forms of this. And hopefully I didn't mess you up with the negative that's distributed inside of there. Okay. Now, when we evaluate this one, now you can see this is an infinity divided by infinity. When a goes to 0, this will be infinity. When a goes to 0, the 1 over a will be infinity. So now I can use L'Hopital on that. So this will give me the 2 still out in front, the limit as a goes to 0 from the right of, I'm just doing L'Hopital this guy. I can't get rid of this negative 1. So this is plus, the derivative of natural log of a will be 1 over a. Of course, the derivative of 1 will be 0, and I'll put this negative in there with that. And then the denominator will be negative a to the negative 2nd power, which means this will be 2 times the limit as a goes to 0 from the right. This negative 1 is still in there. And then this would be multiplied by my reciprocal. This would be, just get my signs right there. That should be a plus a, which of course, as a goes to 0, is going to go to 0. And I have a 2 times negative 1, or a negative 2 for the value of this one. That was a little bit convoluted, but hopefully you can follow that if you need to go back and look at the video a couple times to get it. hopefully you can figure that one out. Next one, you'll see we have an issue because our upper bound is infinity. So we'll write this as the limit from 1 to b of the natural log of x over x squared dx. Don't see a u substitution in here, but I do see a possibility for a u v prime in here. So if I make u the natural log of x, remember our acronym to help us remember this, logs are the first ones to choose here, which means that our v prime is going to be this x to the negative second power. Because remember, this is based upon u times v prime dx. That's our uv prime format that we're looking for, which means I can take the derivative of this. U prime will be 1 over x. The antiderivative will be add 1, multiply by the reciprocal. And then we just have to follow our format. The limit as b goes to infinity doesn't go away. And first term, I'll put this in parentheses, will be the u, oops, I put a prime there for some reason. That should not have a prime on. This should be v, because the first term is always u times v, which would be the natural log of x over x. Oops, I forgot my negative there. And then I subtract, and since I have this negative here, this will become positive, and this will be 1 over x times 1 over x, or the integral from 1 to b of x to the negative second dx. I think we can go ahead and do a quick little antiderivative of this, and we'll be good. Change colors here on you. So this is the limit as b goes to infinity of the negative natural log of x over x. That doesn't change. We've already evaluated that. But this one's a simple little power rule. Add 1 multiplied by the reciprocal and evaluate from 1 to b. The limit as b goes to infinity of negative natural log of b over b minus 1 over b, and then we'll have to subtract the natural log of 1 over 1. Well, that's just going to be, well, I'll write it in here, natural log of 1 over 1 minus 1 over 1, which is 1. Okay. Natural log of 1, of course, will be 0. When b goes to infinity, 1 over b will be 0. Oops, but this one is an infinity over infinity, which means we need to do L'Hopital here. So that would mean the limit as b goes to infinity, the derivative of natural log of b will be negative 1 over b. And of course, the derivative of b will be just 1. And I do have this guy still hanging out here. Okay. Remember, this one was 0. This one was 0. I'll distribute this negative, so this should be plus 1. When we evaluate this, and again, this was the derivative of b, that's a 1. And this is 1 over b. And when we evaluate this at infinity, 1 over infinity means this term is going to 0. And as a result, we get 1. Okay. So you can see that some of the main focus was for you guys today to learn this p-test and how that can shorten our converge and diverge process to just, yes, it diverges because of the p-test. A special case was the e-test. And then I did a few more examples based upon what we've done on the first unit and from all of the last units. A little tic-tac-toe, a little substitution, and some UV primes are necessary. All of these were improper, so I had to write the limits. This one was improper from the start, and I probably should have written a limit on there, but when I did my use substitution, that took care of itself, and I didn't have to worry about the limit on that one. So I did notice as I look at it right now, I probably should have rewritten this as a limit as a goes to 0, because we do have a 0 down there in the denominator, but that can be, that was easily fixed when we did our use substitution. Okay, so all right, have a wonderful day. You will find the homework matches most of this, and I will talk to you tomorrow.